Ready?
Yeah.
Oh, hello. Welcome to another Learning Glass Studio recording. Today we'll do a problem on steam tables, which is related to using water. And as engineers, we're interested in this because water is a very useful working fluid for mechanical work and heating. And it also applies to water in the air and things like that. But today we'll talk about how to use steam tables and phase diagrams to analyze a process of heating water. Okay, so as we talked about, we can use a phase diagram to map out the states of water in terms of the pressure and volume. In this case, it's a specific volume, so it's the related to the density. It's the opposite of the density. The inverse of mass density is specific volume. And here we've shown that we can also map this out in terms of temperature. So both of these look similar, where there is a region bounded by this dome here called the saturated liquid vapor dome, where the inside, this is a boundary where you have a tipping point between liquid and vapor mixture, and on this side it's a tipping point between vapor mixture and vapor for both the pressure volume phase diagram and temperature volume phase diagram. And we're talking about specific volume, meters cubed per kilogram. Okay, so let's talk about using these tables or this phase diagram to quantify the energy used to have heat transfer into a system of water and then boil it and keep on heating it all the way through phase change. Specifically, we'll talk about constant pressure boiling. And you can picture this as this water inside this piston cylinder assembly, where this piston moves up or down. In this case, let's say it moves up because there's some heat transfer in, and let's say this piston moves up so that the change in pressure equals 0, so it's isobaric, and that means the only way that if you're increasing the energy, that will cause some either phase change or some expansion, and there's going to be an increase in volume to keep the pressure constant. So this is the water that we're talking about here. Okay, so the question is, how much heat transfer in to boil water, specifically between these two states. So given that state 1 is at a temperature, known temperature of 100 Celsius, and the pressure at the beginning, which is also the end, it's isobaric, constant pressure, will be 232 kilopascals. And since it's isobaric process, so the pressure is going to stay the same. And then if we follow these lines, the pressure is going to be the same on this temperature map as well. So state 2 is going to be a hotter temperature though, because it's heat coming in. Let's say T2 is 200 Celsius, and P2 again is P1, which is 232 kilopascals. All right. So we're going to analyze this going from an initial temperature, this heat transfer comes in to keep the pressure constant, this volume changes, and the final temperature is 100 degrees hotter. So we know that this is water, and when we don't know the state of the waters that we're working with, the first question to ask is whether we are on this boundary or somewhere inside the middle, because we don't know where we are. We can be compressed liquid, we can be superheated vapor, or we can be anywhere in between. So the fastest way to answer that question, the question being, is state one, are we liquid or mixture or vapor? How do we answer that question? We compare the states that we are to the mixture region and go from there. That'll tell us whether we're relative to mixture, whether we really are liquid or vapor. How do we do that comparison? Well, we can look at the temperature first. So at the T1 we're given, we can ask ourselves, okay, at this temperature, what is the saturation condition? Meaning that if we were to be at this temperature and saturated, meaning either saturated liquid, saturated vapor, or somewhere in between, if we were at this temperature, saturated, there's only one possible pressure we can be. That can be, that's called Psat. There's only one possible pressure that can be saturated. If we are as 100 degrees C corresponding to a saturated condition, that means Psat, the pressure we are, has to be Psat. So if we look at the steam tables for this temperature, Psat is 101 kPa. So our pressure is different than that. At 100 Celsius, we're at 101 Celsius. To be saturated somewhere in this dome or on the borders, we have to be at 101 kPas. We are not at 101 kPas. We are actually larger pressure than that. So the pressure we are actually at is higher than Psat at this temperature. So what does that mean? That means we have to be compressed liquid. If it was equal, that means we would be saturated liquid, saturated mixture, or saturated vapor. If it was lower than this, the only way you can be a lower pressure than saturated is if you're a vapor. If you're greater than that, the only way is to be compressed liquid. Another way to look at that is you can say, okay, let's fix the pressure. So the pressure we are at given is 232. Let's look at it from that perspective. First, we looked at it from the temperature perspective. Now let's look at it from the perspective of pressure. If we are at this pressure, the only way to be saturated is you need to be at a certain temperature, Tsat. What is that temperature? Let's look on the pressure table. So this would be table A4. Let's look at fixing pressure. Let's find Tsat from table A5. That would be 125 Celsius. Since the Tsat does not equal 100 Celsius, we're actually 100 Celsius. That's not the Tsat. That means we are not at the saturated condition. And if, in fact, if we compare, our actual temperature is lower than the saturation pressure at this. So that means from a different perspective of table A5, we're at compressed liquid. So we use two different methods to pin down what state we are, which is compressed liquid, and that will give us the values of properties that we can use to analyze this problem. So if we want to know the properties at state 1, we can look at the state compressed liquid table. But as I mentioned in class, I'm not going to give you the compressed liquid table on the exams. I'll give you the saturated liquid table. So, but no compressed liquid table I'm going to show you today how to use a saturated liquid estimation. Should we do that now? Yes, let's do that now. So we just established that we are at 100 Celsius, somewhere here, and because our pressure is higher than the saturated pressure, then we are in this zone. So if we were to draw a line of 232, constant pressure line, we know we are constant pressure. So let's say this is 232 kilopascals, and the way that this phase diagram works is that this will be the same pressure, same pressure, same pressure, and the temperature increases as you go towards this increased volume or decreased density. And then when you undergo the phase change, both the pressure and temperature stay flat with each other. You keep this phase during the saturated region of phase change, you have both the temperature flat and the pressure flat. But once you go into the superheated vapor region, to keep the pressure constant, you would have to increase the temperature and increase the specific volume. So this will be the line where here it's 232. Here it's P equals P sat equals 232. Here as well, P is superheated. But the difference is that our temperatures change. So we are given that at the end, our temperature is 200 Celsius. And at the beginning, it's 100 Celsius. So to keep the pressure constant, we keep on increasing the energy, and we go through this phase change region. And so the question is, where do we end up? I gave you a little spoiler alert here. But before we do that, how do we get the values of the properties without a compressed table? Well, let's do an approximation that for compressed liquid, the internal energy and other properties equals a function of temperature and pressure, but it's a pretty good approximation to say that it's only a function of temperature. Weak on pressure, meaning that it doesn't strongly depend on pressure. So what does that mean? Well, here's the algorithm to estimate the properties from the saturated liquid table. What you would do is is you would find where T1 equals T sat, or the other way around, T sat equals T1 on P pressure table. This is A5 that I posted to Canvas, not in our Rasher Piro book. It's the more detailed tables that I posted on Canvas. So we know that the temperature is T1. So we go to the pressure table and we ignore the pressures, but we look for the temperature sat column and we look for T1 on that column. And when we do that, so for T sat, then use those values. Use that row of values. So for example, where T sat equals 100 Celsius on the P table, you can read off values that you can say UF is the values of the internal energy on this branch, the fluid branch. UV would be the table of values on this saturated vapor branch. And if you're in between there, you would have to know the quality. Since we're estimating the properties of compressed liquid with the saturated liquid, what we're saying is we're going to use the values on this saturated liquid branch of F column to estimate the compressed liquid. So we can read off UF at this 100 Celsius row is 419 kilojoules per kilogram. Let's just say that is, by this physics, U1. And similarly, BF on that column is 0.001 meters cubed per kilogram, and that's basically V1. So what did we just do? What we did was we said we are actually here on this 232 line, we're actually in this compressed liquid region. And by the laws of physics invested in me, we said that only the temperature matters. So if only the temperature matters, then basically all of these properties at the same temperature are similar for liquids, both compressed liquid and saturated liquid. So let's take it all the way to this borderline, which is these F values on the table at 100 Celsius. So this would be, let's call it 1 prime. This would be our estimate. That's what we just did. We use the saturated liquid table, meaning the saturated mixture table has both liquid and vapor, and we pulled from the F column, which is liquid. And now we know the internal energy at state 1 and the volume at state 1 by making this approximation. Okay, what about state 2? So for state 2, we are given that we are 200 Celsius at the same pressure. So let's do the same comparison that I'm erasing now, but for state 2, and go from there. So by this properties, we need to know the properties at state 1 and the properties at state 2. That will give us the change in the state of our system. That can be used by the first law to figure out what happened in between. That's where we're going with this. And since we don't have a ideal gas equation or heat capacity or other model to get these states, we're using tables. Okay, so again, state 2, it's T2 equals 200 Celsius, P2 equals 232 kPa. So solid, liquid, or vapor, well, if we go from the perspective of temperature using table A5, table A4, then that will tell us, the question would be, what would be Psat at 200 Celsius? And if we look that up, we would see that Psat is 1555 kPa. So what that tells us is that definitely we're not saturated, because 1555 does not equal 232. And in fact, P2 is smaller than Psat at 200 Celsius. So that means, what does that mean? It means we are superheated vapor. So we are not in this region because the known pressure we know where we are at is not Psat at 200 Celsius. Psat is higher. That means we're superheated vapor. So we know we're 200 Celsius, and our pressure is 232. The only way that can happen is you're somewhere out here. So as I said, this is the final state. Here is state 2. 200 Celsius and 232 kilopascals. We could also look at that from the perspective of pressure. So at P2 equals 232 Celsius, we can look at table A5 and find out that if we were at 203 kilopascals and saturated in this region, there's only one possible temperature. That temperature is 125 Celsius. We are not 125 Celsius. In fact, T2 is greater than Tsat at 232. That means we have to be superheated vapor. So drawing this out here, state 1, we are at 232. Let's call this 232 here. And the way that the temperatures work out is that at constant temperature, be like this. Wait, yeah, do that. Something like that. So, as a matter of fact, this is 100 Celsius. T equals 100 Celsius. So it's 100 Celsius here. The pressure goes down to keep the temperature constant, and then during phase change, the temperature of both pressure, the temperature and pressure both stay constant. And then when you're in the gas phase, the pressure decreases for the same temperature as you go this way. So these are lines of constant temperature. And where we are is somewhere in between, where at state 1, we are 100 Celsius. At 232, the only combination has to be in compressed liquid space. And then in this piston cylinder, there's energy increasing, and it takes us into the phase change region. But as we just looked in the steam tables, the only way to be 200 Celsius is to fall back on this temperature branch here, all the way in the superheated region. So these are the 100 temperature isotherm, and this is the 200 Celsius temperature isotherm. And what we did in this cylinder is we started here on this temperature branch, then we increased the temperature as we increased the energy, then the temperature stayed constant in this region, and then we went into the superheated region where we caught up to this 200 temperature branch. And so that's how it looks like on here. Here's how it looks like on here, on this two different phase spaces. So we went through compressed liquid to saturated mixture across both boundaries into the superheated region. And that's what we did here as well. This is how it looks. We increase the temperature. You can see that here. What we're doing here is we're going across many of these different branches of the temperature. Same here, except we kept on the same pressure branch. This was isobaric. So even though we were in the phase change, liquid and vapor, the temperature changed here, but not the pressure. We kept on this isobaric branch. Here, we had the same pressures, and we went across two different temperature branches, or many different temperature branches here, then it's constant here, and then we crossed a few temperature branches here. Stuff like that. Okay, so this table is straightforward. We can look that up. We know the temperature, we know the pressure, we know we're superheated. We can look up on table A6, superheated vapor table, and look up those values. What are those values? Is that U2 equals 2653. Do a little bit of extrapolation because 232 is not directly on there, but by extrapolating, we find that V2 is 0.960 meters cubed per kg. So if we compare the volumes, both the energies, superheated vapor has a much higher energy than saturated liquid at this temperature. And the volume is greater than the saturated liquid value. So it makes sense. If you're superheated vapor at a higher temperature, you should have a higher energy. That makes sense. And specific volume, what this means is it's the inverse of this density. So it's either it takes up more space, gas takes up more space per mass, that makes sense. Or if you look at the other way, this has more mass, liquid has more mass per volume than gas. So that's what we're saying. That is intuitive there. Okay, so we have the values. Now what? Well, let's use this in the first law. So the first law on closed system. It's closed, there's no reactions, so let's write the first law in terms of delta U. And there's no kinetic energy, no potential energy change, so it's just simply Q minus W. First law. Okay, so delta U, the temperature changes, so there's going to be a delta U change. We know that there's heat in to boil the water. Let's describe this in terms of little q per mass, because that's what our steam table is, and we don't know the mass of this water. work. Does the boundary change? Yes. To keep the pressure constant, the boundary moves, so the volume increases. So this is, yes, delta V greater than 0. So it's work out, and pressure is constant. So if we want to know the heat transfer, delta U plus W. Well, okay, we know delta U, this is U2 minus U1 plus W. And if we write this in more details, Q equals, U2 is superheated steam, so superheated minus U1, which is what we estimated as a sat liquid. So we found those values already, UF, sat liquid, plus this would be work equals the integral of P dV, but for constant pressure process, it's V2 minus V1. So this would be P cool. We know superheated internal energy. We found that from the steam table. We know saturated liquid internal energy. We found that from saturated liquid table. And this is a good estimate for the compressed liquid that it actually is. We just pulled from the saturated liquid to get a similar answer. It's basically the same if you can check it out. And okay, and we know the volumes as well. The superheated vapor table gave us V2, which is much more space or much less density. So this would be V2. Here would be the compressing, or it's more compressed at the beginning, or takes much less space at the beginning. So we know those. Okay. So let's do this on the side. Work. I'll erase this here. Let's do this work calculation separately because the units are pressures and volumes. How do we relate it to energy? Well, this is how we do it right here. So if the work equals pressure times V2 minus V1, that would be 232 kilopascals, the pressure units, times V2, which is 960 meter cubed per kilogram, minus 0.001. So let's call it 0.959 meter cubed per kilogram. What does that have to do with energy? I'll show you right now. So I'll do this unit conversion like this. So what does 1 kilopascal equal? 1 kPa is 1 kilonewton per meter squared. So a pascal is a newton per meter squared. So I'm doing a ratio here where this equals that. So it's a ratio of 1. And if I do it this way, this will cancel out here. Okay, so we have kilonewtons. And we're basically done because now we can cancel out that these 3 meters cancels out the 2. You're only left with 1 meter left. And that's basically joules, kilojoules. So 1 kilonewton meter equals 1 kilojoule. So the meter here cancels this meter here, the kilonewton here cancels this, so now we have kilojoules. So that's how kilopascals times meter cube per kilogram gives you kilojoules per kilogram. So work equals, if we calculate that out, 222 kilojoules per kilogram, little u. So that was the last thing we needed, in a good way. So U2 is 2653. U1 minus U1 is 419. Then we just found work plus W, which would be 222. And this is all kilojoules per kilogram. And here we can double check. This is a positive number. That means that you get its work out. That makes sense because delta V is greater than 0. So this should pop out a positive number. That's good. The volume increase, that means that the water did work on the surroundings because the volume increased. That's a general rule to remember. And that gives you a positive number. That's good. And then when you plug in a positive number here, everything should work out with this convention of Q minus W here. That means net work out. Okay, so yeah, then we do the algebra, and if we do this algebra, we should get that Q equals 24. So all this for this, that's good. And then to work out the logic as well, this is a positive number. So Q is greater than 0, that means heat in. That makes sense because to boil water, you have to put energy in through heat transfer. So that worked. All these numbers popped out. So what we did was we used our initial temperature and pressure we are given and our final temperature and pressure we are given to find the properties of the water, and those properties happen to be all over this compressed, all over this saturated vapor dome, meaning that it was started off as compressed liquid, ended up as superheated vapor, and we used this dome properties to figure that out. So we didn't know we were at compressed liquid at the beginning, but we compared it to the saturated liquid properties, and that tells us whether we're left or right, up or down, whether we're compressed or superheated. So state 1 happened to be compressed because the temperature was lower than the saturated condition, and state 2 was superheated because the temperature was higher than the saturated condition. And then that tells us where to go on the tables. So the first table was compressed liquid, but we applied this estimate because compressed liquid only depends on temperature as a good estimation. So as long as we use the same temperature at this saturated condition, all those values are similar. Excuse me. Those values will give you good estimations of the properties. So this is how it looks like on the pressure. It's isobaric because the cylinder can move up and down, and that allowed us to follow this process on this PV diagram. And because the volume increased, in this case the piston moved, there's some work involved. And it's an isobaric process of work transfer given by this. And then we knew all those from the steam table, all the properties we needed. And then here's a conversion between pressure and volume to give kilojoules. Okay, so that wraps it up, and I will see you again next time. Thank you.